In this video, I'll discuss a couple more things about matrix operations and do a couple quick examples. If you'll remember from vectors, when you take the dot product of two vectors, say v and w, v dot w is the same thing as w dot v. But what about with matrix multiplication? Is the matrix A times the matrix B the same as the matrix B times the matrix A? Well, in general, the answer to that is going to be no. So the fact is, it is not true that AB is always equal to BA. Now, you may be able to find some coincidental examples where that is the case. But it's easy to come up with examples where it is not true. Let's just take a quick one. Let's take 1, 0, 1, 0 and 1, 1, 0, 0. Multiply that together and you get a matrix that entirely consists of ones. Remember how we do matrix multiplication to check this. We take row and we dot product with column. That will give us 1 plus 0. And then we take row dot product with the next column. That gives us 1. We would take row dot column and row dot column, giving us all of these ones. Now, if you take instead 1, 1, 0, 0 and multiply it times 1, 0, 1, 0, well, 1, 1 dot product with 1, 1, this is going to give us this new entry 2. And 2 is not equal to 1, so these matrices are not equal. There are some coincidental examples where it is commutative, and one of them is given below. But in general, it's just not going to be true that AB is equal to BA. Next, I'd like to run through a couple of quick examples to demonstrate matrix multiplication a little bit further. Let's look at a matrix A, and then let's write down a squared, a cubed, and a formula for a to the n. The purpose of this example is just to demonstrate what the exponential notation for matrix multiplication means. So if I have a squared, what that means is I'm just going to take the matrix A times the matrix A with standard matrix multiplication. So here in this example, I have 1, 1, 0, and 1. And you can work out this first case of A times A and see that you get 1, 2, 0, 1. Well, I am going to claim that as long as we're taking n greater than 0 here, A to the n is going to be given by 1, n, 0, 1. Well, how would I arrive at such a formula in general? Well, it's a fun and easy inductive argument. So let's write this out. You can get this general formula by induction. Well, we've actually already worked out the base cases, a to the first power and a squared. So our base cases are done. Base cases where n is equal to 1 and 2 are good. The formula holds. So in an inductive argument, what you would do next is assume that the formula is true for n minus 1. In particular, if we look at a to the n minus 1, it would be 1, n minus 1, 0, 1. And then we use this assumption to prove the formula in general. So then a to the n means a multiplied times itself n minus 1 times, that's a to the n minus 1, times 1 more a. And that's a to the n minus 1 times a, which would be 1, n minus 1, 0, and 1. So you multiply this again times 1, 1, 0, 1, and carefully work out the matrix multiplication, and that is, of course, going to give you 1, n, 0, and 1, and then you would be done. The second example that I want to discuss is more of a remark than an example, and that's that a vector can be thought of as either a 1 by n or an n by 1 matrix, depending on whether you're writing it out as a row or as a column. And whether you treat it as a row or a column can give you a very different type of matrix multiplication. So let's look at it in one way. Let's look at it in the dot product way. This is what I mean by that. So I'm going to first take my matrix written out as a row. This matrix is a 1 by 3, and I'm going to be multiplying it by a 3 by 1, a row times a column. A row times a column is the same thing as a dot product. So when I matrix multiply together, I'm going to get the specific entry, 2 plus 2 minus 3, which is 1. And that's just a single number, and I'm thinking now of a single number as being the 1 by 1 matrix that I get. My dimensionality rules tell me if I have a 1 by 3, and I multiply times a 3 by 1, these numbers have to match, and these numbers are going to be the dimensions of what results, a 1 by 1 matrix, which is essentially just a scalar. But what if I were to flip it around and take a 3 by 1 times a 1 by 1? In this case, I get something very different, something called outer product. In the previous little example, we were doing a dot product, and dot product is also called inner product. Well, if I do it the other way around, it's what's called an outer product. So now I'm taking a column times a row, and I've rearranged things so that now I'm taking a 3 by 1 times a 1 by 3. And my dimensionality rule tells me that these match, and therefore I can multiply them, and the product is going to be a 3 by 3, whereas before I had a 1 by 1 product. And now I need to be a little bit careful as I work out what exactly this product is. So how is it that I take these two vectors and I get all 9 of these entries? Well, this first entry 2, where this comes from, is by taking 2 times 1. I'm taking the first row times the first column. It just so happens that my first row only has a single entry, and my first column only has a single entry. And then I take 2 times minus 2 to get the minus 4, and I get 2 times minus 3 to get the minus 6, and so on and so forth. So to use a different color, where does this minus 2 come from here? Well, that's going to come from taking the third row and the second column. That's a 1 times a minus 2, giving me this minus 2. So here's how I produce my outer product of this column vector and this row vector. So I have a third example that I want to do. In this problem, we're going to solve the matrix equation AX equals 0, where A is the specific matrix that is 2 by 3 with these entries. So the solution that we want to find is X. We want to find the vector X to solve this system of equations or this matrix equation. Well, the first question we need to ask ourselves is, well, what size is X? What are the dimensions of X so that this even makes sense? And while we're at it, what are the dimensions of this 0 vector as well? Well, let's see. A here is 2 by 3. So that means that the number of rows in X need to be 3. So that means that X is going to have to be a 3 by 1. That way I'm taking a 2 by 3 times a 3 by 1. That way these inner terms match. And this is going to be giving me something which is a 2 by 1 0 vector. And a 2 by 1 0 vector has entries that are all 0, and there will be 2 of them. So it'll be something that we write like this. So let's go and solve this now. And the way we're going to solve it is by using Gaussian elimination on an augmented matrix. This is a simple example, and there aren't many steps to the row reduction algorithm, so I'm going to just put them all here simultaneously. We take our initial matrix, which is the matrix A, and it's not strictly necessary to augment it by the 0 vector because zeros don't change, but I'm going to do that just to make it more clear what's happening in this problem. And we follow row operations until we've put it into row reduced echelon form. For this particular example, we're going to take minus 2 row 1 plus row 2. That's going to turn this entry into a 0. We're going to follow that up with a 1/7 times row 2, which just makes the second row look a little bit simpler. And then the third row operation, 2 row 2 plus row 1, is designed in order to kill this minus 2. You see, once you get to here, you're already in reduced echelon form. And so this is the point at which you start moving upwards in your elimination procedure. We started moving down, and then We finish off by moving up in terms of elimination. All right, that's who we're killing here. All right, and we end up with a matrix that looks like this. All right, in the first part of the matrix, let me erase that circle and put a different one. In the first part of the matrix, we have something that looks an awful lot like an identity matrix. But there is a column of entries that we can't really simplify any further right here. Let's assess what we have going on. When I look at this, I see that I have two, what I'm going to call pivot columns. We haven't described the concept of being linearly independent yet, so I hesitate to use that language. But I have two pivots that are ones, and they occur in these first two columns. So I have these two pivot columns. But then I have a third column, and I can write down a relationship that describes column 3 in terms of column 1 and column 2. So when I look at column 3 is the column vector -1 7 and -4 sevenths, which is the explicit linear combination of -1 7th as a scalar times 1 0 plus -4 sevenths as a scalar times the vector 0 1, which is a scalar times column 1 plus a scalar times column 2. So this is -1 over 7 column 1 -4 over 7 column 2. As a system of equations, I can also write this down. So it might be easier to think of this as a traditional system. And if I wrote it down in that way, I would have x1 minus 1 7 x3 being equal to 0, because this is a homogeneous system where everything's set equal to 0. And x2 minus 4 7 x3 is equal to 0. And writing it down like this, I see that I have x3 as a free variable. It could be anything. But x1 and x2 depend on x3. When I go and I parameterize my system, I need to give a name to my free variable x3. So I would write down a general solution to this system of equations in the following way. A general solution is going to be x1, x2, x3, where, let me use the color purple here, from here, from all of this here, let's make that a little neater. From all of this here, I have that x1 is 1 7 t, x2 is 4 7 t, and x3 is t, where t is the name that I've given to my free variable x3. So that when I write this in vector notation, I have my x1, my x2, and my x3 appearing here as the coordinates of the solution vector x. There's lots of different ways of expressing this solution vector. As an alternative, I could write it like this, as a column vector, x1, x2, x3, where those entries are given here as the entries of this column vector for t and r. Another correct way to write this would be as follows, because this is the same thing up to scalar multiplication. So we've now solved this system of equations. And we started with something that was a matrix equation, but our method for finding the solution was the same old Gaussian elimination.